Our next speaker is Boris from Nvidia. Correct? Boris,
I will do my best. All right, let's see. Okay, and just like that, we're live. All right, so hi everyone. Thanks again for coming. And my name is Boris, and as Alex said, I'm a research scientist now at Nvidia Research. And in particular, today I'm going to be talking about how to more effectively integrate prediction within the autonomous vehicle, the modern autonomous vehicle stack. And the reason I want to talk about this today is because there has been a ridiculous amount of research focusing on trajectory forecasting. And I'm showing here a graph from the fantastic review paper that I think everyone in here should be citing and has probably been talked about a few times. So yeah, thank you, Andre, and everyone else, and you know, Luigi, and everyone in this room. And you know, there's been hundreds more published since that review was released. And I want to say, there's a lot of great work that's been focusing on improving method runtime, accuracy, output diversity, etc. And there's also been a lot of different ways to incorporate external context like maps or agent dynamics. But one thing that I always want to point out is that prediction methods don't operate in a vacuum. And this really especially rings true for autonomous vehicles, where the inputs come from perception and the outputs influence motion planning. And unfortunately, there hasn't been as much research on how to effectively integrate these modules together. And so today, what I'm going to be talking about is actually exactly along this front. I want to be talking about how we can more effectively integrate prediction with the rest of the autonomy stack. And I'll be focusing on that in 3 different ways. The first is like the literal integration of the different modules together. Then the second, and I'm glad this question was asked recently, I want to talk about evaluation metrics that can actually more holistically capture how you can actually evaluate a method's integrated performance. And then finally, I'll talk about some future directions that I think are really high yield, but as of yet, under investigated for maybe some of us in this room to take a look into. So without further ado, I want to start by talking about integration. And in particular, integrating different modules in autonomy stacks very quickly becomes a question of robustness and addressing uncertainty and error propagation. And so I want to start by first focusing on how we can integrate prediction with perception. And perception, as we hopefully all know, can be quite noisy and can be quite uncertain. And this uncertainty, very quickly just propagates through the rest of the stack. And I'm showing here some examples of, if we have some noise in detection, it can affect tracking, which can then affect prediction, which then affects planning and control. But then we also use those detected objects in planning and control and et cetera. And so, one good thing is that, our group, both, at Stanford and now at NVIDIA, we have been looking at quite a few of these directions in terms of bringing some of this uncertainty and, a lot of models in perception, like object detectors or trackers, will give you uncertainty. And so we've been looking at directions for how to actually incorporate this uncertainty into prediction and then also propagate it downwards onto planning and control. One particular task that I'll be focusing on today is that connection between tracking and prediction. And this is really the question of how can we make prediction robust to tracking errors, which are quite commonly fall into 2 classes. One is called fragmentation, and the other is ID switches, where basically your tracker is confusing one object for another because they're close by or because of occlusions, reasons like these. And I'm going to be focusing on 2 works today, which tackle this problem. But really, I first want to just start by saying that for all the research that there has been in object tracking or detection and tracking, it's really, there's still quite a few mistakes that are made. And this is, this is on Kitty, right, which has existed for a long time now, and for which there have been a plethora of methods published just solely on this data set. But as we can see in this video, there's still lots of ID switches, lots of fragments over time. And these, when you track them and when you have these mistakes, they can really detrimentally affect prediction. And to show like a concrete example of what this looks like, when we have predictions with accurate tracking, we can see on the left here that this vehicle in yellow is, we can predict some very sensible, paths moving forward. The vehicle is probably going to continue moving left, given it was just finishing a turn. But on the right, we can see what happens when you have a false positive detection very near the vehicle, which then causes an identity switch. This now makes it to the forecaster seem as if there was some high acceleration change of direction, which then causes predictions to wildly swing, right? And because these mistakes happen quite often, we really want to be robust to them, especially in prediction, which is then very close to planning and control. And when we quantitatively measured this on two different data sets that are typically used for this, we saw that prediction errors are very, very detrimentally affected. And we still don't really have good answers for how to tackle these this kind of question of integration. So today, the main question that actually I want to ask, which is tackled in one of our the latest work that I'm presenting here, which is published at CVPR and will be soon presented, is tracking even necessary to make predictions? Because the main problem in tracking is that you have to make these hard associations between different time steps in order to say, okay, this object belongs to this detection, and so and then you kind of keep unrolling this. But do we actually need to make these hard associations in order to make accurate predictions? And so the key idea that we were investigating in this work was, can we just directly use detections and their similarities over time, also known as affinity, directly as prediction inputs? And this was the core question we had. And we have like a transformer architecture here with a specific attention mask inside that can take into account, that can directly take these, smooth affinity values. And we found that when we do indeed kind of do away with hard object association, prediction errors drop drastically, especially in the face of tracking errors. And to show qualitatively what this looks like, here on the left, I have prediction results from like a standard tracking prediction pipeline using state-of-the-art components. And then on the right, I have our method, which just directly takes detections and their affinities between frames as input and outputs predictions. And what we can see here is that really a lot of the errors that occur on the left side, you can see basically like because of ID switches or false positives and fragments, there are some predictions that just kind of errantly appear. Whereas on the right side, you see nothing, or you see just normal predictions coming out of of the vehicle to wherever it's headed. So this is kind of one, these are the kind of core questions that I want to pose in terms of when we combine different modules together, how can we maybe avoid some of these information bottlenecks between them? So switching gears a little bit, looking a little bit more downstream at the integration of prediction and planning, I want to talk again about this interface, this informational interface between them, and focus in particular on the information representation that we very commonly use in this field, which is agent tracklets. And agent tracklets are exactly this kind of set of waypoints of where a vehicle will be in the future. And this is a very common, very sensible output, especially given the evaluation metrics that we use in the field. The problem is that a lot of planning and control methods, they don't reason about agent tracklets. They usually reason about system dynamics. And so usually when you're trying to combine the two, you have to make some trade-offs in terms of, okay, well, if I have a tracklet, then maybe my MPC, I can maybe have some weird collision avoidance term or something. And then you always end up making these trade-offs where really, maybe it's better to take a step back and ask, can we just have a different output representation through trajectory forecasting that plays nicer with planning and control? And this is exactly the question we asked a few years ago now, which was basically, can we produce this, a different prediction representation that is cognizant of the downstream use case of planning and control? And in particular, what we were looking at here is rather than producing directly, future positions over time, can we produce a system dynamic representation of a scene's evolution? And really what I mean here, and like the way that we implemented it, is that we produce the coefficients of a linear time varying system or mixture thereof, especially because we want to have multimodal predictions as well. So we produce these coefficients, and then you can use, by rolling out these system dynamics, you can still produce agent tracklets. So we were able, of course, to compute all the normal evaluation metrics. But when we combine this with a simple MPC routine, it was much, much, much faster to use this linear time-varying system to then compute, for example, collision avoidance constraints, or to compute, acceleration and jerk limits and stuff like this. And so, this is, again, tying into this theme of, rethinking the information bottlenecks between modules. These are like some ways that you can more tightly integrate different components. And keeping with this like theme in mind, something else we've looked at much more recently is actually adding more structure to the outputs of predictions to, again, make them more friendly for planning. And so one kind of annoyance with the previous method that I proposed was that, well, it's outputting a linear time varying system, which, I mean, it's not as expressive as a full deep neural network. And so we did have to give a little bit in terms of performance, like in terms of raw prediction performance. And so in this work, which is again another CVPR work, which is going to be presented in a month, what we were tackling in the group was focusing on this, the fact that we want to output scene consistent predictions. And this is important because when you're planning, if you're predicting the motion for all of the vehicles, and now you have some collisions in the scene, I mean, now it's going to be very strange for your planning control module to reason about what it should do. And so the two core things that we wanted to keep in mind were that we want to predict scenes without collision, but also we still want to have multiple different modes of how a scene can evolve. And so here, even though, if you just predict the marginals of each vehicle, it's very reasonable that they'll just continue forward. But when you reason about collisions, you now realize, okay, one is probably going to yield in front of the other. And so this is kind of some of the modes of enumeration that we might have in this scenario. And the way that we tackled this problem and the way that we kept in mind this kind of informational representation is that basically we like this idea of outputting multiple modes and using deep neural networks and et cetera. But in order to avoid like a combinatorial explosion of realizing about how each agent will react with all the other ones in the scene, we grouped agents into cliques, into basically cliques of agents for whom they're kind of all interacting with and will very likely have similar motions in the future. And so I'm showing you an example here. The colors represent different clique assignments. And so here we can see these vehicles on the very left at time equals 0 seconds. These blue vehicles, I mean, they're all approaching the intersection. One is probably going to slow down and something. And so they're all going to kind of slow down behind that vehicle. And then in the next time step, or a few time steps later, we can see that these cliques can also change. I mean, to be fair, agents, as they're moving, as they're, they might interact with different vehicles. And we can see, for example, this new like purple vehicle on the bottom left, it's a little bit farther away. And so it might not be, interacting as closely as those blue vehicles are with each other. But something else that's very interesting with this type of structure is when you still maintain like, your internal, like, all of these are built upon conditional variational autoencoders. All of these are built upon this internal probabilistic latent space in order to handle multimodality. What's very nice about, building like a fully kind of this distributional architecture is that you can actually now set some of these latent values yourself and reason about counterfactuals. So here I'm just showing just a rollout from the model with no conditioning, nothing at all. This is basically just taking some history time steps from a scene and then rolling it out in the future. And I mean, you can see because there's even some, some hopefully minor mistakes of, cars running a little bit off road or something as kind of the prediction model is losing the plot a little bit. But then if we condition on these two circled vehicles slowing down, we can see some very interesting behavior where now the brown and purple vehicle behind them actually have to slow down to react. And this is very nice because, when they are approaching them, when they're coming close, they become part of the same clique. And now we can reason very nicely about their joint behaviors, again, while still avoiding that kind of combinatorial explosion if you try to model the entire scene with one as one group. Okay, so switching gears a little. So that was kind of talking about the like direct combination of things in the stack. I want to talk about evaluation because this is another way that you can combine different parts of the autonomy stack and holistically evaluate them, even if you might have different modules. So the main question that I want to ask here, and I'm glad someone else asked it earlier, was how can we measure an autonomy stack module's performance? And I want to say that we can actually do this at least independently. You know, for perception, there's a lot of metrics. For prediction, there's a lot of metrics. But what happens, what falls apart a little bit is when you now integrate them together, if I have a low, you know, IOU, or if I have a very high IOU detector, does that mean it's going to be an excellent detector for prediction, for planning control? If I have a really accurate predictor with very low ADE, is that going to lead to excellent plans? I don't know. It's still a little bit up in the air. I would hope so, but it's still a little bit up in the air. And the reason I say it's still a bit up in the air is because all of the, you know, evaluation metrics that we're currently using are purely accuracy focused. They're trying to compare an output prediction to some ground truth, like what actually happened in the scene at that time. But the problem is that with this, you know, when you have like task agnostic metrics like this, you miss some of the asymmetries that are actually inherent to the problem of driving. And I'll give a few examples here using prediction and detection. So in prediction, you know, let's say here we have, you know, some human vehicle in gray turning right, and then we have, you know, some ego vehicle, like our autonomous car, on the top. If you have some prediction errors, and here I've drawn a kind of a circle around the endpoint. So I can say here, okay, all these prediction errors, like this purple and green prediction, they are wrong by the same amount, at least if you compare them metrically via an accuracy-based metric. But the core difference is that if the mistake that you're making is this purple prediction, well, now that seems much closer. That seems like a very scary mistake because it actually might cause your ego vehicle to enact some type of safety preserving maneuver if you think that someone's actually going to be coming very close. Whereas that green prediction is not going to change anything about your car. It's a harmless mistake, so to speak. And even in detection, this same type of problem can exist where, you know, you might have some detections that are just a little bit wrong, which might seem, you know, like a vehicle is a little bit ahead or a little bit behind. And we have a big asymmetry here in terms of downstream effect. And so in one of our latest works at the Intelligent Vehicle Symposium that we are going to be presenting soon enough, we looked at, you know, how can we develop task-aware metrics which actually take into account these outcome asymmetries, which are really inherent to driving. And I think there are 4 key desiderata that we have for any metric to be a task-aware metric. So of course, we wanted to be able to capture these asymmetries that I was talking about earlier. And then you know, while we want them to be task-aware, I think very importantly, we want to develop metrics that are method agnostic. If I want to evaluate how good some prediction is for planning, but then I use RRT star or something like that as my planner, anyone else who's not using RRT star cannot really use this planner, or it's kind of locked to this one method and it might be missing, you know, elements from other types of planners that, you know, might have different, you know, internal structures which make them behave in different ways. Now, of course, we also want these to be computationally feasible to compute so that at least you can compute them over huge data sets or collected driving logs. And we also want them to be, and I'm using a very overloaded term here, interpretable. Interpretable, I don't want to really dive into so much of the meaning of the word here. I just mean, I don't want to use something like a deep neural network where I have absolutely no idea if it says, oh yes, this is, you know, this is like a task safe prediction, why, or like, you know, or this is task unsafe. And if I can't just look at it and be like, okay, I have no idea how to debug this or work with this. So I just use that 4th word to mean basically something that's at least, you know, some engineer can actually use to interpret what to do next. And so the way that we looked into actually implementing like a proof of concept that follows these desiderata was a 2-stage process. So in the first stage, you know, again, to rid ourselves of focusing on one particular method, we first started by learning a proxy planning cost function that accurately reproduces recorded vehicle motion. And the reason we chose to do this is because, you know, at least in my mind, planning cost functions are kind of one level of abstraction above a planning method, because many planning methods will minimize some cost function, but you can use many different methods to minimize the same cost function. So at least in my mind, there's kind of that one layer of abstraction. And then once we have such a cost function, we take its gradient with respect to perception, for example, detected objects, or predictions. And it basically, this gives you a measure of planning sensitivity, i.e. how much your plan would change if your detection or prediction changed. And kind of when you roll this process out a little bit, this is actually kind of what it looks like. Is, we start with some human motion data and then a set of cost function terms. And then through inverse optimal control, we can obtain, planning cost function weights that then, give you, this linear combination of them to give you a final cost function, which we can take the gradients of. And when we actually do take a look at what, these gradients are, when we take a look at the magnitude of this, which we call planning sensitivity, we can see some kind of interesting, outputs already, which are, for example, we can see that false positives are actually captured by this method and actually pointed out to be kind of highly planning sensitive. So here, the way the colors work here, by the way, and this is a little bit confusing, I'm sorry for that, but every detection here is going to be, the color slides from red to yellow, where yellow is like highly planning sensitive and then red is like not planning sensitive at all. So we can see, on the very left image, when we have a false positive detection, like right next to the ego vehicle, that's going to be very planning sensitive. And then on the other side, same thing, when we have like a bicycle kind of falsely detected next to the vehicle, that's also going to quite heavily affect motion planning. On the right, we can also take a look at how, future motion can affect, we can take the gradient with respect to predictions. And on the right, we can actually capture some very interesting scenarios where our model pointed out that, hey, this future motion could affect the, ego vehicle a lot. And so, we can catch, for example, the fact that, if a pedestrian suddenly decides to cross the street, like on that very top right image, that will necessarily affect the ego vehicle. And I think in the data set, the ego vehicle actually has to slow down to react to it. So kind of the fact that you can catch this a little bit early makes it very nice from like an evaluation metric perspective, because you can capture this, this is exactly the asymmetry that we want to capture. Now, I realize that all I've talked about is this like planning sensitivity, but I haven't said anything about how can we use this in a metric. And so actually, finally, after you do this entire, hopefully not too arduous process, we can take this measure of planning sensitivity and actually inject it into existing metrics to make them more task aware. And in particular, there's kind of two ways we looked at least in this paper, to kind of provide examples. So the first way is kind of internally. You can, for example, change some internal parameter to change internal metric thresholds based on planning sensitivity. So the example I give up top here is, if you're computing a precision recall curve for detection, something that you can do when you compute this precision recall curve, you have to internally have some metric of like how far away is your bounding box from the other bounding box in order to say that it's like accurate, it's like to match the detection with the ground truth. And what I did here was I basically just said, you have to be more accurate for objects that are highly planning sensitive. So it's kind of, I assigned a bit more importance to those objects. And you can see on the left is kind of the normal precision recall curve. And then on the right is what happens when I bring in this scaling. And you can actually see that the performance drops. Like, the area under these curves is smaller. And then there's also external ways that you can use planning sensitivity to measure performance, where you can kind of, from an ad hoc perspective, you can say, okay, what was the performance of my, for example, prediction method here? In particular, I was analyzing Directron++. What is the performance of this prediction model on on vehicles with different sensitivity or pedestrians with different sensitivity? So for example, what's comforting to see here is that Directron++ actually performs best on agents that have high planning sensitivity. So it's kind of, it would be very scary if like its worst performance was on like very important agents, right? That would be kind of, oh man, I kind of need to go back to the drawing board here. Okay, so I also want to outline now these last few minutes, I want to outline what I think to be kind of high yield future directions that I think are really like holding the field back in terms of preventing really like a huge expansion in the deployment envelope of behavior prediction. And one thing that I presume many speakers talked about today, and you're probably quite familiar with, is that many prediction models, they produce uncertainty. And unfortunately, they also assume that their inputs are known with certainty. And so they don't really take into account the fact that there is upstream uncertainty information that they can take into account. And then number two, like I said, a lot of them produce uncertain outputs, but these uncertainties are rarely, if ever, calibrated. And I think this is something important if you actually want to use something, some of these outputs for something like motion planning. Now, today I discussed a few of our works that address this first point, but I think there are very few approaches tackling point two. And I think this is where, some new ideas would be really appreciated. Another, core question is module co-design. So, I talked a lot about today about this informational bottlenecks between the different modules. And I'll be honest, I actually argue that the interfaces between modules are arguably more important than the modules themselves. It's very, it happens a lot if you have an excellent object detector, but then you have a trajectory forecaster that maybe can't use all the information. It's kind of wasted, right? You could just use some other type of method and you wouldn't really even see a difference downstream. And the kind of questions, that I want to ask here are, what kind of information should be passed between components? What makes a good X for Y? And for example, what makes a good object detector for prediction and planning, or what makes a good predictor for planning and control? And then even, other questions could be like, how should modules be architected together? So for example, I gave this very classic waterfall look of okay, well, prediction, object detection goes into prediction, goes into planning and control. But if there's nothing to say that, if you have a fast predictor, you should actually just be using it in your planning control loop, because then you can at least evaluate, maybe in a proactive sense, you can evaluate how can other agents react to my motions, and what will happen if I do this? What will happen if I do this? So this is another area that I haven't touched upon, but I think these are the kinds of questions that we need to discuss. And then lastly, this is a very classic machine learning discussion, but I think the vast majority of papers that I've seen in this field are evaluated on only one or two data sets, maybe three if we're lucky. And I think the question I always have, even when reviewing them, is how will they fare in new environments? How will they fare with new agent types? How can they be deployed safely if they've only been maybe trained on a small amount of data from a specific geographic region? And I think the other thing is, are there going to be core external factors that actually require our attention? Or are the typical machine learning tools of early stopping, dropout, regularization, et cetera, are they good enough to kind of generalize, have these methods generalized? And as one example, I want to say that the new scenes data set contains both left and right-handed driving, collected from Singapore and Boston. So I think I think if methods are working there, then maybe maybe there's other structural factors that maybe we need to consider. And actually, towards this point, I want to say that we're definitely at a really good time in the field. When I started back in 2019, there was really only Katie, new scenes was just released. That was kind of the big kid on the block. But now, we have many data sets of 1,000+ hours of data, which I think is really, there's been a significant growth. And I think there's a lot of these data sets that we can use as researchers. However, and I've tried to use them, I swear, but all of them have a different, unique format. And oh man, is that really frustrating when you want to try and take something you've worked on for 3 months just to spend 2 weeks trying to use some other input. And so something that we're working on and that I'm actually quite close to open sourcing is we're developing at Nvidia, or at least in my team, a unified AV prediction data loader, where the core idea is to provide one access point for many different data sets with a single, simple, hopefully simple API to really speed up development for different methods in the field. And besides just making our lives easier, I really hope that it kind of enables new lines of research, like analyzing prediction generalization. So yeah, stay tuned. It will probably be in this GitHub, but still waiting for a little bit of approval internally, but that should be happening soon. So yeah, in summary, I just want to say that three key points. Prediction doesn't operate in isolation. I think we really need to keep in mind that its inputs are generally perceived in the real world and its outputs influence downstream components. Evaluation metrics are a little bit lagging behind the applications of prediction methods. And I think it's still, as of yet, quite difficult to evaluate different components holistically without implementing the entire stack. And then finally, even though there are autonomous vehicles driving around today, I want to point out that there are many, many open problems in the field. And I think they really all necessitate further research. So, I just want to say, if any of this sounded interesting to you, we're building a great team in Nvidia, which, hopefully may include you in the future. So please check out our website. And yeah, I hope you all found this insightful. Thank you very much.
Questions? Yes.
You can yell it and I'll repeat it.
Yeah,
It's good to. No,
thanks for the very nice talk. So I was wondering, you mentioned the cost function from the motion planning, and that's one way to take into account how this affects. But what about the constraints? Because the cost affects the constraints. So did you take the collision aware as constraints and put them as a Lagrangian in the cost function, or how do you reason about that?
Thanks for the question. Yeah, so I'll just quickly repeat. So the question was basically, I talked about this cost function and how we can use that to bring kind of this holistic sense of information upstream. And the question was basically, okay, so cost functions are great now. How did you take into account constraints? For example, collision. Did I take into account the Lagrangian in the collision function or something like this? In that specific work, we basically just had penalty terms in the actual cost function, but there weren't any. We didn't do anything like specifically like bringing the Lagrangian of a collision term. I basically just, in this work, we just wanted to kind of pose this idea out there and say, here's like an example cost function with some example terms that actually well reproduces human motion behavior and, could be a nice starting point. But I think something like collisions is, we're absolutely looking at not even just collisions, but also rules of the road, like, laws and stuff like this. I think this is a big open area that we're definitely interested in looking into. Thanks for the question. I think it's the same two from the chat. I can see them. So,
Any Zoom questions?
One question.
Oh, yeah.
Sure. So, thanks for the talk. I really like the idea of your applying sensitivity metric. It seems to me that because you're using the planning cost function for different tasks that are kind of originally designed for, there might be some assumptions baked in there or some sort of like consideration we might want to think about in terms of like probably the upstream or designing cost function.
Yeah, that's a good question. So just very quickly to repeat, there was a question on, we looked at using cost functions to bring information upstream, but cost functions, as you rightly pointed out, they're built to be minimized to reproduce to generate motion, and there might be things that you have to change about them in order to actually capture more about the problem of human motion at the downstream level to then propagate stuff. Yeah, I think I'll repeat a little bit of what I said before. Basically, we just wanted to there was two things we wanted to do with this work. Was basically one, point out that metrics are not good enough as they are for this kind of work, and secondly, to pose this kind of one potential option. I think, yeah, like there's a lot that you can add, and I didn't, at least with the paper, we didn't want to go into the level of like, oh, can you like reward hack some like super complicated function? Because I think, yeah, there's so many terms like traffic laws, rules of the road, maybe different hierarchies of like, right of way, stuff like this, like, which it's hard to capture in just a single function. And I think also I should say, like one planning cost function, that's like not realistically how like a lot of vehicles move, right? They have quite complicated like if else hierarchies and etc. So I think this is, I think, what was missing in our work is bringing that real, like a real sense of like a real world planning and control architecture, which captures information. But yeah, again, I think a ripe area for future work. And it's a good question. Thanks.
How do you capture the effects of the action of the ego video in the responses that are made by the other agents?
Oh yeah. So the question was, are we taking into account in our prediction methods,
Yeah.
the effect that the ego vehicle's motion plan will have on other agents. Absolutely. So with every single prediction work, which funnily enough, I didn't even talk that much about prediction in this talk, but every prediction work that we've worked on in our group at Stanford and that we're using in our group at Nvidia, we have always this ability to pass in the ego vehicle's future motion plan, with the idea being that your outputs are now, your like predictions are conditioned on this. And the idea that you can, for exactly as you're like thinking, the idea is that you can now evaluate, like for example, if you're doing sampling-based motion planning, you can sample like a batch of, I don't know, 100 ego vehicle motion plans, and then like compute the, let's say 100, like one prediction for each of them, and then evaluate, I don't know, some cost function if you want, and then pick the best one. So yes, this is absolutely something that, you know, our methods can do.
Great.
I'll hand it back to you. All right, thanks everyone.
Thank you. That's great.